Going to look at a practice question set number 24 on diffraction gratings that we had due this morning. The first question says, in a laboratory experiment, a microwave generator is used to produce a beam of monochromatic microwaves. We say monochromatic, one color, right? Color we usually think of as red and orange and yellow and green and blue, indigo and violet. Color just really means frequency, right? Color with invisible light is red, orange, yellow, green, blue, indigo, and violet. But when we talk about monochromatic, it doesn't necessarily have to be visible light. It means one color, one frequency. And here we've got microwaves that are one frequency. These waves are incident on a series of metal tubes that form a diffraction gratings. The metal tubes are spaced 1.8 centimeters apart. I don't know what just happened there. What do you think this 1.8 centimeters corresponds to? What variable is that? The metal tubes that the microwaves go through are 1.8 centimeters apart. It's not X, somebody said. It's going to be D, yeah. This is the distance between the openings, the distance between the slits. Okay, we're just dealing with a bigger opening, and we're dealing with a bigger opening because we're dealing with a bigger wavelength than we're used to dealing with, right? Usually we got visible light. Okay, this time we got microwaves, which is a smaller frequency and a bigger wavelength. If we've got a bigger wavelength, then we can afford to have bigger opening and still make this work. When the microwave signal passes through the grating, a receiver placed 52 centimeters from the grating detects the maximum signal. That's going to be L. Okay, the receiver is going to be our screen. Okay. First order maximum signal is also detected at each of positions 1 and 2. So this would be our central maximum. Okay, this would be our first order maximum, and then this would be our first order maximum on the other side as well. And of course, it says it's not drawn to scale. We do have an angle given here. It's 49.8 degrees. Clearly, we're going to call that theta. Clearly an angle that's significantly bigger than 10 degrees. So we know we're not allowed to use that lambda is equal to xd over n times L equation. That's okay. It's not an issue here because we know that since we have the angle, we're going to use the d sine theta equation anyways. We want to find the experimental wavelength of the microwave in centimeters. So let's go lambda is equal to d sine theta over n. Now, notice we want to find the wavelength in centimeters. Okay, what can you do as a little bit of a shortcut here since you want to find a wavelength in centimeters? Since all the data that's given to me here is in centimeters, you could actually get away with using just centimeters. Look, there's only one of those values of distance that I need, okay, and that's going to be d. If this is going to be centimeters, then this is going to be centimeters as well. So I can leave that as centimeters if I want. 1.8 times sine of 49.8 degrees divided by n. What would n be? If the angle between the central maximum and either of the first order maxima, position 1 or position 2, is 49.8 degrees, then n would be equal to 1. Good. Okay, the danger here is making n equal to 2 because we look at this, all right, first one, that would be 2, right? But we're measuring the angle not from this one to this one, but from the central to the first one on either side. Good. When we do the math there, what do we end up getting? What is it, sorry? 1.37 centimeters. Now, if you had to convert this to meters, 0.0180, that would be fine. Yeah, that's the standard, right? Then we would have gotten 0.0137 meters. Then we would have had to convert it back to centimeters. So this is just a tiny bit of a shortcut if you catch that. Okay, if in doubt, if you're not sure when you can leave the units in centimeters or whatever, just go to meters because it always works, right? Just go to meters and then convert back, that's all. All right, next question. And this is a gooder here. How many people got this one right? Okay. Students use various apparatus to investigate optical phenomena. During their investigations, they make the following 8 observations. And we've got 8 observations here. We'll read through each of them, but let's see what the question is first. It says 4 observations that could be produced using only a triangular glass prism are numbered what? Okay, using only a triangular glass prism. When you read through these, you're going to see that it's basically as opposed to a diffraction grating. Because diffraction gratings and prisms will do almost the same thing, right? They'll split up light. If you've got white light shining on a prism, it splits it up. Okay, like the poster over here, if you've got white light shining on a diffraction grating, it will also split up as well, although the pattern ends up being a little bit different. Okay, and you can see that as you read through it, 1 and 2 kind of go together, 3 and 4 kind of go together, 5 and 6 kind of go together, and then 7 and 8 go together. So we're going to pick one from each pair here. Prism, not diffraction grating. When we shine white light through a prism, does it produce a continuous spectrum? A continuous spectrum, by the way, is the rainbow, right? Red, orange, yellow, green, blue, indigo, and violet, transitioning from one to the other, as opposed to a bright line spectrum where we have one color and then a distinct other color. Does a prism produce a continuous spectrum or a bright line spectrum? It's a continuous spectrum, yes. White light produces a continuous spectrum. Does the apparatus produce an interference pattern with monochromatic light? No. A diffraction grating produces an interference pattern, right? With monochromatic light. But a prism produces a single bright line with monochromatic light. Okay? The one color goes through and it produces a single bright line on the other side. Does the apparatus bend red light through a smaller angle than it bends blue light? Red, orange, yellow, Roy G. Biv for the prism, Viv G. Yor for the diffraction grating. It bends red light through a smaller angle than it bends blue light. A diffraction grating would bend red light more than it does blue light. And finally, number 7 and 8, the apparatus produces a single spectrum when white light is incident on the apparatus, or produces multiple spectra. Well, if you have a prism, again, as you can see on the wall over there, it's going to produce a single spectrum, a single rainbow. If you have a diffraction grating, you know that it produces multiple spectra, right? Because a diffraction grating has the first order maximum, that is all the colors, and then it has the second order maximum, it's all the colors, and so on and so on and so on. Okay, 1 spectrum, 2 spectra, 3 spectra, and so on. Multiple spectra for the diffraction grating. So the answer would be 1, 4, 5, 7 for this one.